from this discussion, in order to run a cycle, we should have three main kind of things. The first one is heat source. Okay. And second one is the cycle. And the third one is heat sink. So all the essential part of the thermodynamic cycle analysis is to think about how these heat source, cycle, and heat sink are interacting to get what you want out from the cycle. So let's try to make an example. Okay, so I'm going to take a steam power plant as an example of a type of thermodynamic cycle. Even though we are going to learn a lot more details about a steam power plant or a Rankine cycle, just if you look at really briefly about how this plant is made of, we can find out as a main component a pump, a boiler, turbine, and condenser. And now this boiler is considered to be a heat source, or there is a certain heat transfer from heat source to the cycle in terms of Q in. Similarly, we have a condenser in a steam power plant as a component that rejects heat to the environment, in the case heat sink, such as the atmosphere or river or ocean and so on. Now, we have to remember what is the objective of having a steam power plant. So the objective of having a steam power plant is to generate the power, so generate the electricity by running a turbine. So in order to run a turbine, we need to have a steam that is at very high temperature and at a very high pressure. So that's why we have a pump and turbine. So now let's just briefly explain what's going on inside a steam power plant. In the case, water is our working fluid. So water gets to a pump, and the objective of a pump is to increase the water pressure to very high pressure. So now at the exit of pump, water is highly pressurized and flows to boiler. And as you know, boiler actually can generate a steam out of water. So at the outside, at the exit of boiler, now we have a steam where its pressure is very high already, thanks to pump, and also the temperature is also very high because of boiler or heat transfer into a boiler from heat source. And now this high temperature and high pressure steam goes to turbine and run a shaft by rotating a rotor inside, and as a result of it, this turbine should generate a power. And then a steam gets to, after using all this kind of energy to turbine, its steam goes to a condenser where the remaining heat is rejected by cooling that water, the steam down to water. Then this water goes back to a pump to make a cycle. Okay? Now, as you see, we have three main components. One is energy source or heat source, and second one is heat sink, and in the middle we have a cycle, in the case a steam power plant. And now in order to run this steam power plant, we need to run a pump, and we get a power out of the turbine. Then what you can think is the W net out or net work output from a steam turbine can be written as W out, in the case turbine work, minus W in the case pump work. And always this should be, we want it to be positive, otherwise there's no reason that we should run a steam turbine, because the more we run it, the more money we spend without nothing. But at the same time, this steam turbine should have certain heat input from heat source, and we reject heat out from steam turbine to heat sink. So if we write out the net heat in, I'm not going to write in here, so Q net can be written as Q in minus Q out. Okay. Now, with that being said, let me generalize what we just discussed, by taking an example for steam power plant to general heat engine cycle. Now, if we generalize it, then we can draw such a schematic like this. So now again, we should have heat source, high temperature. Let's say that is TH. And as we already discussed, this temperature shouldn't change because that is a reservoir. And also we have heat sink, that is TC. Then in the middle, we have a heat engine cycle. It can be, a steam power plant for that example. It can be, car engine. It can be, anything that we can think as a heat engine. Again, in order to run this heat engine, we need to get certain heat input from the heat source. Sometimes I'm gonna use QH. So it should be the same because that is heat that comes from heat source. Then what this heat engine does is by using this Q in, then we generate a power out, and that is what you really want to have. That is all sole purpose of having heat engine cycle for our own good, right? And after we generate a power, there is still a remaining heat, and this remaining heat should be rejected from heat engine to the heat sink, and that is again sometimes I used QL. Now, if we set up your heat engine as our system, the first law of thermodynamics can be written as this. So the change of internal energy inside of your heat engine during the thermodynamic cycle should be 0 because you have always the same initial state and final state as far as you talk about a cycle. And now that is balanced with net heat in minus net work out. Okay. Now, from the heat engine perspective, this net heat in can be again written as Q in minus Q out. So what I can write it out as a result, as a conclusion, is the net work output from the thermodynamic cycle or heat engine cycle should be balanced as Q in minus Q out, right? That is really important equation that you have to remember. And from this base equation, now we can calculate the power or work output. That is the first essential part of the performance. Now, is that all? In the, basically now, so we have an engine. So we can have this power out of this engine. But another question that we always have to ask as an engineer is that how efficient it would be. So now, how efficiently can we, generate a power by having the heat input to that heat engine? So in order to discuss that further, now we have to define a thermal efficiency. Or in other words, because we mainly use a first law of thermodynamics to define the thermal efficiency, that is called as first law efficiency. Now, in general, the thermodynamic efficiency or let's say the thermal efficiency is defined as the desired output versus required output. So that is very general definition of a thermal efficiency. Now, if you apply that general definition to heat engine, what is our desired output? Why do we operate the heat engine? So the desired output of a heat engine is, again, net work out, right? Then in order to get this net work out from the engine, what do we need to do? What do we need to invest? What do we need to input to the system? So required input in the case is the amount of heat that should be transferred into the system from a high temperature heat source. Now, with that being said, the thermal efficiency of heat engines is defined as this equation. So we basically compare how much net work is produced from this heat engine when we have certain heat input to the heat engine cycle. And in terms of equation, we usually use N sub TH, which equals to the amount of W net out divided by the amount of heat in. And now from the previous page, we know that net work out is same as Q in minus Q out. Okay? So by inserting this equation to that equation, so now we have 1 minus Q out minus Q in. That is general equation of the thermal efficiency for heat engines. Then let me highlight it again as the second essential, very important equation about the thermodynamic cycle analysis. Okay. Now, here we go. So many times, you may have to design a cycle. So like design a kind of a heat engine, or sometimes you want to do performance analysis of the heat engine. Now, when you do those kind of tasks, always what you have to focus on is two parts. Okay, one is how much work you can produce out of this heat engine. But that is not all. How efficient it is. You always have to do these two both. Okay? And here's a very simple example. So let's say that we have a heat source and we have a heat sink. Now we have two heat engines. Okay? So one engine is here, like let's say the engine 1, and there's another engine 2. And now we have the same amount of heat input to these engines. But engine 1 produces only 20 kilojoule as a work output, while the other engine 2, produces 30 kilojoule as a net work output. So which one is better? So in terms of work output, engine 2 is better. And as a result of energy balance of the cycle of the heat engine, now the remaining 80 kilojoule should be rejected to heat sink for engine 1, and 70 kilojoule should be rejected as a waste heat to the heat sink. And now by applying the equation of the thermal efficiency, the thermal efficiency can be calculated for engine 1 to be 20%, and engine 2 has an efficiency of 30%. So for this very specific example, engine 2 is better than engine 1 in both the power output point of view and for the thermal efficiency point of view. But it should be noted that this is not all the case. Many times, the net work output does not go along with the efficiency. So what it means is basically, if you want to have a high power output, many times you have to sacrifice efficiency. Or if you really want to achieve a high efficiency, then many times you have to sacrifice the amount of power output. So they are not going along. Many times they just go opposite direction. So you have to make a wise selection, wise choice, based on what is your objective.